This is problem 17 from chapter 22. Compute the actuation force required for the short shoe drum brake of figure 2217 to produce a friction torque of 150 foot-pounds. Use a drum diameter of 12 inches, A equals 4 inches, L equals 24 inches, friction coefficient equals a quarter, and B equals 5 inches. What are they talking about? Well, you've got to go back and look at the figure. So we're looking for figure 2217. And the figures given in the problems are figures that begin with the letter P. If you go back, let's see, to page 707, here we go. Look at page 707, and you'll see various configurations for short shoe drum brakes. Okay, so we know the frictional torque, we know the drum diameter, we've got the length of the handle, the A offset, the B offset, we have all those things. So frictional torque, I'll just jot down the givens up here, 150 foot-pounds. The diameter of the drum I'll label D sub D, 12 inches. The A dimension 4 inches, B dimension 5 inches, and the length of the handle 24 inches, friction coefficient quarter. Okay, now the solution to this is essentially the equations on page 707 as well. These are pretty straightforward. Equation 2216 and 2217 are the important ones. In fact, I'll begin with the actuation force. Excuse me. I'll begin with the actuation force, which is 2215. Now, 2215 and 16 are the same equation, just rearranged. So, since I don't know the actuation force here, that's what I'll use. Now, to get the actuation force, I'll have to have the friction force and to get the friction force, I'll have to get that from the friction torque. So the two equations I'm using are essentially 15 and 17. So the friction torque is the friction force multiplied by the diameter of the drum over 2. Now, what are these things? Where did they come from? Well, actually, both of them are moment equations. This equation represents the moment of the frictional force on the drum. This equation is derived from a moment equation based on the moment that WL causes. You can see how you could rearrange this equation, just putting the length of the handle on the left-hand side. And basically then this moment causes an application of friction force to the drum, but that application is not just as straightforward as frictional force times B. It's not quite that simple. And the reason it's not that simple is because if you think about it, you apply force, let's put a pivot here, you apply force here, you're applying normal force to the drum, right? Because of the friction coefficient, let's say that the drum's rotating in this direction. Because of the friction coefficient, there's going to be a frictional force in that direction, right? Because you're trying to impede the motion. The relative motion's in this direction, so your frictional force goes in the opposite direction. Now, consider what this does, because this is a frictional force on the drum, right? But there's an equal and opposite frictional force on the pad. What does that do? That tends to work against the applied load W, right? So this takes away from the moment being caused by this. Now, on the other hand, if the drum is rotating in the opposite direction, now the frictional force on the drum is in this direction, and the frictional force on the handle and the lever is in the opposite direction. So now, notice how it's causing a moment in the counterclockwise direction, just like the applied load is causing a moment in the counterclockwise direction. So you have to take that into account. Both of these affect the amount of normal force and therefore the friction force. That's why this is a little more convoluted. Does that make sense? So that's where that comes from. Anyway, so putting this back where it was in the equation, the first thing we'll do is calculate the frictional force because we know the frictional torque. So the friction force that we need to apply to the drum to make this work is 2 times the friction force, or the friction torque, divided by the diameter of the drum. Just rearranging this equation, 2D on the other side. So let's see, 2 times 150 would be 300 foot-pounds. The numbers are really straightforward, so we'll just do this in our heads. The diameter of the drum is obviously a foot. So you can see that the frictional force required is 300 pounds in order to apply the required torque to the drum. So now that we've got the frictional force required, we can answer the question, which is how much load has to be applied to the handle to get the thing to work. So since the frictional force is 300 pounds force, what you'll notice is that the units here, this is basically a geometry factor, those units will cancel out. So A is 4 inches. The frictional force is dimensionless, it's 0.25. B is another dimension that is 5 inches. On the screen still. And then L, the length of the handle, is 24 inches. Now you have to be careful because notice I just changed the diameter from inches to feet because it was convenient, but I didn't change the length of the handle because I've already got inches in the numerator, so there's no need. So that way they cancel. So 4 over a quarter is like 4 times 4 is 16. 16 less 5 is 11. So we need 11 over 24 times 300. So go ahead and throw that into your calculators and let's see what you get.
137.5.
I'm sorry?
137.5.
137.5, yep, that's what I got. So there's the actuation force required to produce that much frictional torque. What about if we didn't put that much force on the handle? What would happen?
Wouldn't stop.
Well, we wouldn't get that much frictional torque. We'd still get frictional torque out of it, but not that much.
Yeah, you wouldn't.
Okay. Any questions on that problem? Okay, as a designer, if that's too high of a force, what could you do?
Reduce the length.
Well, if you reduce the length of the moment arm, you're going to hurt,
It's increased.
right? You'll increase the
You
length.
said if that force is too much. I
If
think I
it's-
misunderstood you, sorry.
You were thinking if the frictional torque is too much. I'm saying if this required, this is how much the person
Oh,
has to
increase
push.
your length, yeah.
You could increase the length, but there's something more clever that you can do. What if you don't have space?
You can reduce the frictional torque.
Friction
Well, you
material.
can't change the frictional torque. That's what's required to slow down the load.
Can you change friction material?
That would only change the friction coefficient. And that would change this denominator right here. That may be difficult. What else could you do?
Dual pads?
How about messing with this A and B? Do you notice that the amount of load required is really sensitive? In fact, you could balance these two such that the amount of load required to apply that handle is 0. Because to make this difference 0, then the amount of load to the handle required is 0. Do you understand what A and B are? If you don't, you should look at figure 707. Those are 2 dimensions that are important in moment calculations.
So in order to decrease the actuation force, you want to change the quantity of B and
A and B, that's what I would choose, because look, that's just the distance to a pivot.
A. Okay.
So you can easily mess with those, right?
So if you decreased your A,
So if you decrease A, if you get A to 0, then you actually have to pull back on the lever to keep it from applying the brake,
yeah.
right? So a negative force is required.
So if you decreased your pivot point from, if this was friction material and your pivot point's out here, if you decrease that where it's right here,
It's mainly this difference that's important
yeah.
in tuning that. Any questions? Yeah, you're right. Since it's positive, you need to decrease A.
Yeah.
You're right. All right, that's that problem.